Hello everyone, so in this video let's talk more about this photochemistry. So if you remember in our last video we have talked about the reactions, like how this photolysis affects our reactions. So if you have not watched that video, I highly recommend you to watch it, because basically this video is the second part of that previous video. I will put the link here. Now if you remember, we have talked about the reaction schemes for a particular photochemical reactions. If you now we have our reactants in our ground state. So here I have symbolized it by S0, which means singlet ground state, right? I hope you remember we have talked about in these symbols and these singlet ground states, triplet ground state, sorry, triplet excited state, these things in our like first two videos. This is singlet ground state. Now in photolysis, what we do is we are going to expose these molecules in the ground state to photons, or otherwise the light. So we use light to irradiate it into the higher excited state. So here we have the singlet excited state. Then what happens is this singlet excited state will form the reactive intermediates, right? Here we have the reactive intermediates. Now based on the mechanisms, there can be several reactive intermediates, right? So this is the first reactive intermediate, and there can be the second reactive intermediate, and then the products likewise. So the amount of, the steps of reactive intermediates, how many reactive intermediates are available in the particular reaction, will depend on the whole mechanism. So for now, let's assume we have only one reactive intermediate. Okay, here we have only one reactive intermediate, and then this reactive intermediate will results in products. We have introduced two terms for this particular reaction. Here this term, the formation of the reactive intermediates from the excited state, we call it as primary process, right? Here we have the primary process, and then primary photolysis, and then secondly we have the product formation from the reactive intermediates, we call as secondary process. Now in this particular video we are going to focus on this primary process, right? We are going to see what is the mechanism, like how we can determine a particular mechanism to form the reactive intermediates, right? How to determine the mechanism of the formation of the reactive intermediates. Okay, so we are going to look at this particular case in this video. Now there are several things you need to think about when you try to identify the mechanism. Now when we look at the primary process of primary photolysis, so this is the process which we are thinking about. We have the reactants in the excited state, singlet excited, and then we have the reactive intermediates. Okay, now the thing is, I will put the it's not also here. These reactive intermediates, right? These reactive intermediates, always remember, when you look at the reactive intermediates, this has the characteristics of the excited state. Otherwise, the reactive intermediate will be based on the excited state. So you can look at the reactive intermediates and say whether this reactive intermediate is coming from the singlet excited state or it is coming from the triplet excited state. If you remember, like we have two excited state, right? We have singlet excited state and the triplet excited state. So if you have no idea about the singlet and triplet and the difference of these, I will put the link here for that particular video. You can watch it. Now the reactive intermediates, they are dependent on the excited state which they have formed. Now there are two possible excited state, which are S1 singlet excited state and T1 triplet excited state. By looking at our reactive intermediates, we can say based on the characteristics and the energetics, likewise the properties of the reactive intermediate, we can say whether this is come from singlet excited state or whether it's come from triplet excited state. Now, to determine this mechanism, to determine the pathway of these reactive intermediates, we have to think about four main categories, right? The first thing you need to look at is the energetics. You have to look at the energetics, and then you have to look at the dynamics, right? So the energetic means basically what you have to think about is the feasibility. Now, whether this whether this mechanism is possible or not. So we have two possible ways. No, if our energetically favored process or energetically favored pathway is this one, we say the S1 or otherwise the singlet excited state is the energetically favored excited state. So energetically, this mechanism must follow through this pathway, not this one, right? So we have to think about all these four factors to determine the mechanism for particular reactive intermediate. So this is basically the feasibility. Otherwise, the Gibbs free energy, you know energetics, right? Thermodynamics. And the dynamics means how fast is our reaction. Now, it doesn't matter whether, like, let's say from energetics, we can say that this is possible, right? This is feasible. This process is feasible. That doesn't mean that this reaction happened through this process, because this may be feasible, but it may take a million years to go through this particular reaction. So dynamics comes to play. Even though it's feasible, the dynamics will explain to us that this reaction takes a lot of time. So in our real time, we can't say that we can't see any product is forming. So even though the particular pathway or particular mechanism is energetically favored, it can be dynamically unfavored, right? You understand the case, right? So in that case, we cannot propose this particular mechanism because it's not dynamically favored. It's not dynamically possible reaction. Okay, this is the dynamics. And then we have structure of the reactive intermediate. And finally, we have to consider about the electronics. So in this video, we will discuss about these two terms, which are much more simple and straightforward, energetics and dynamics. In the next video, we will talk about the structure and electronics, which is these two are going to play a huge role in our mechanism determination. Now, when do you look at the energetics? From energetics, what we are trying to do here is we are going to identify in which position of our molecule that the reaction would happen. Like if I take an example, let's take a molecule like this. Here we have a benzene ring. Here we have CH. Here we have Br. Here we have CH2, CH2 and Br. Okay. Now we are going to irradiate it and we are going to do some reactions, right? So after the reaction, some product would be happen. So a question would be asked that what would be the product. Here this is the product A. This A is the substitute, and this is the one who's going to attach to our molecule. This is the product 1, and the other one is this one. This is the product 2. Now our question is going to be asked whether this particular product after the radiation, here we have now the excited one. So the final product, what would be the final product, like whether it's this or this. Now in that case, first what you need to do is you need to identify the chromophore, right? You need to identify the chromophore. The chromophore is the place where your excitation would happen, right? In this case, this benzene ring is the chromophore. Now basically the chromophores are the excitation, that possible excitations, right? So there are 5 to 5 star excitation and lone pairs, into 5 star likewise. These are the excitation. We will talk more about this in details manner. For now I will give you a quick idea how to identify this chromophore, right? So if your molecule has components like this, if your molecule has a benzene ring, right? If your molecule has a benzene ring, that is a possible chromophore. That's a better chromophore. Benzene ring is a very good absorption. It has good absorption abilities for light. Now if your molecule has lone pairs like this one, carbonyl groups, this oxygen has lone pairs and also it has pi bonds, this is a very good chromophore. This is also a very good chromophore. And if your molecule has double bonds or triple bonds, if your molecule has double bond or triple bonds, these are good chromophores. These can absorb molecule. These can absorb light. But a single bond between these two carbon, this bond is not a chromophore, right? These two are not a chromophore. So these are the points you need to identify. We will look more into details about this transition 5 to 5 star likewise. For now I need you to get the idea what is the basic definition of a chromophore. Chromophore is a place where the light can be absorbed, and most importantly these chromophores are like benzene rings, lone pairs in the oxygen, and also the double bonds or triple bonds in your carbon chain. Now that's the first step to identify the chromophore. Now when we look at this particular molecule, we have to identify the chromophore. I hope you can see the chromophore. Here we have the chromophore. Let me take it in another color. Okay, here we have the chromophore. This is the chromophore. Now in this first reaction, what happens is this bond has been broken. Here look at this. This bond has been broken and a new bond is being formed to this particular position. In this case we have this bond is being broken. Now when the excitation happens, the excitation would happen around here because this is the chromophore. What would be the much more feasible bond that can be broken in this particular molecule? Because this bond is much more closer to the chromophore, right? This bond is much more closer to chromophore than this one. So I would say this bond has the higher probability or higher feasibility to be broken than this one. So when you irradiate this molecule and go through the reaction, right, most of the majority of the product would be this, because this bond will be the most possible bond which can be broken, right? So this position can be easily be taken for the reaction, like it can be easily be attached from this our substitute. That's how we determine the mechanism, like that's how we determine the product formation. Okay, so a bond which is closer to chromophore, it's much more feasible or much more easy to be broken, easy to break. That's the thing you need to be identified, you need to remember. And then another case you would ask, like this is the chromophore. Now there are two bonds, right? This bond is closer to a chromophore, and also this bond is also close to chromophore. As I have told you, these single bonds are not chromophores, right? They can't absorb, they are not efficiently absorbing these light, right? So these are not chromophores, but these can be broken based on the excitation. These can be broken. Now in that case, if you have two bonds which are closer to chromophore, you need to choose the weakest one. This is the weak bond, right? This is the weakest bond due to the electronegativity. So there are two factors you need to remember when it comes to the energetics, right? So when it comes to the bond which is going to be broken, when to identify the bond which is going to be broken. So I will put it here. There are two facts you need to look at. First of all, what you need to do is you need to identify the chromophore, right? And then the bond which is closer to chromophore, and the bond which is weaker. This is the bond, these two, the bond which satisfies these two conditions. This is the one which has more feasibility, which has more probability to go through the reaction. So this is basically the energetics. Like this is the what we need to look at when you have the molecule at first place. And then finally, when we look at the dynamics, it's based on the kinetics. If you remember the Arrhenius equation, right? So K, the reaction rate, is equal to Arrhenius constant E and e to the power minus Ea over RT. Okay, so this A is the Arrhenius constant, right? This A is the Arrhenius constant. So generally, this Ea for a photochemical reaction, okay, the Ea for the photochemical reaction is less than 20 cal per mole. This is the basic condition. So when it comes to the mechanism, we are not going to look. We are not going to be more focused on this dynamic aspect. You just need to know that this is the equation where we are going to determine about the dynamics, and this is an important factor. This particular value, this particular fact will come into the play of our photochemical reactions in our next 3 videos maybe. This is important. So I hope you get the idea of the basics. Now this is very important. I hope you get this idea. If you have any problems, please let me know. In our next video we will talk about the other two factors, which is the structure and electronics.